Hello everyone, final exam review. I'm going to try to do it in about 4 parts, I think, from what you have. At the end of every one of the parts, you're going to get the full final exam review scrolling right at the end of that. So let's take a look at that. They got Chapter 1, Tech Math 1, Chapter 1, Tech Math 1. So let's see what they're trying to say here. From the Chapter 1 content that we've done. They want you to evaluate for this one do the entire top, do the entire bottom, and you should be fine. See what we got here. Entire top. The additions and subtractions always get done at the very end. 4 times negative 7 is negative 28. Negative 9 times negative 6 is positive. Negative 9 times negative 6 is positive 54. 54 and negative 28. 54 and negative 28 is 26. Negative 2 times 5 is negative 10. Negative 10 and 9 is negative 1. Negative 26 is your answer. Again, I always try to double check these myself. Make sure I'm not leading you down the wrong path with this. 2, they are asking you when x equals 2 and y equals negative 3 to evaluate this right here. You know, the best way to do it whenever you're in doubt is put brackets, put parentheses around all items and then go for it. X is 2. X is 2, y is negative 3. Y is negative 3. Don't make any moves here until the very end. 2 squared is 4. Minus, we'll deal with it. 2, just work right here. 2 times 2 is 4, times negative 3 is negative 12. 3 times negative 3 is negative 9. Minus a negative 12 is plus 12. Plus a negative 9. 4 and 12 is 16. Plus negative 9 is 7. There you go. 3. Write as a single power. 4 to the third. 4 to the 0. Times 4 to the negative 7 times 4. Well, times 4, 4 is the same as 4 to the 1. Add all the exponents and you're all set. 3 plus 0 is 3, plus negative 7 is negative 4, plus 1 is negative 3. That's it. Let's see here. 4, the wavelength of red light is 0.000065 centimeters. Write this in scientific notation. Go to a number between 1 and 10. How about 6.5? How far of a walk do you take to the left? 1, 2, 3, 4, 5. Absolutely, you're done. That's 4. Okay. 1, 2, 3, 4. Let's just make sure it's there. It should be fine, guys. I've got negative 26. See if we can figure this out. Got negative 26. I got 7. I got 4 to the negative 3. I got 6.5 times 10 to the negative 5. Sounds good to me. Let's go to the Chapter 2 type content and take it from there. Let's talk about it. They're saying for chapter 2, solve this particular equation. We'll take it from there. Well, okay, I tell you what. Y itself is 1y. Minus 1y is plus a negative 1y. You don't have to go this way. At the end, you just got to solve this thing. Let's see what happens. Let me add a positive 1y on each side. That's out of here. You got 10 right here. You got 4y. Again, you engineer it in such a way that you get rid of what you want to get rid of. You got 2 plus 4y equals 10. Subtract 2 on each side. And there you go. There you go. 2. They want to solve the following. It's a lot of rules. We have to know all of them. Got to be able to work with them. Whenever you're in doubt, adding, if there's subtraction present, adding the opposite is probably a great idea. Is it the only way to do it? No. There's a lot of ways to get around these problems, but usually, if there's an array of subtractions going on somewhere, even if it's just one subtraction, adding the opposite, converting everything to addition is probably the best way to go. Most straightforward way to go. Minus all of this is plus the opposite of all of this. Minus 7 is plus the opposite of that. Watch how fast this goes, how well this goes. Four is 4. Negative 5 times 2r is negative 10r. Negative 5 times negative 7, right? Here's the negative 7. Negative 5 times negative 7 is positive 35. It just makes things a lot easier when you've converted everything into addition. See what we can do here. 4 and 35, leave the negative 10r. Not bad. There's a number of ways to go here. I'll tell you what I'm going to do. Negative 10r and 10r is nothing. 3r and 10r is 13r. You know where this is going. Maybe a few minutes ago even. Divide by 13 on each side. And you got r equals 3. Again, the big move of being able to convert everything into addition is probably a great idea. Look at how smoothly things go. Trying to keep track of subtraction symbols, especially multiple subtraction symbols, can be a big problem. Convert to addition is probably not a bad idea. 3 is saying, write as a single power. Forgive me, no, I already saw that. Another 3 here for chapter 2. 3, if an object is dropped, the distance it falls d in feet in t seconds is given by d equals 16t squared. How long will it take an object to fall 400 feet? Basically, they're saying, see how we're going to do this, guys. I mean, basically they're saying here that this is the equation that's going to get you there, to everything you need. Well, if it falls 400 feet, if d is 400 feet, and this is 16, and this is t squared, solve for t. Not a bad idea. What you do here is divide by 16 on each side. T squared equals 25. You know where this is going. Square root each side, you get plus or minus 5. I'm not talking about negative time here, guys. I'm talking about positive time, and we're getting this for an answer. So, for Chapter 2, problems 1, 2, and 3 are 2, 3, and 5 for answers. 2, 3, and 5 for answers. 5 seconds at the end for an answer. Sounds good to me. Let's look at Chapter 3, and they've got some interesting insight regarding that. Let's keep going. Kind of Chapter 3 type content. They want you to solve (7w over 5) minus 3/4 equals 0. Sounds good to me. There are numerous ways to go here, guys. Definitely numerous ways to go. There's always numerous ways to go, it seems, right? And oftentimes there really are numerous ways to go. Let's see how this is going to play out. There's a lot of ways to go. A lot of ways to go. You could. This is just for the. Let's do this. Tell you what I'm going to do. Why don't you add 3/4 on each side? Add 3/4 on each side. The negative 3/4 and the positive 3/4 cancel, and you end up getting 7w over 5 equals 3/4. 0 plus 3/4 is 3/4 over here. Negative 3/4 and 3/4 is 0. The 7w over 5 is what holds. At this point, based on what I've discussed earlier, you can do cross multiplication. 4 times 7w, you're certainly not distributing here because it's straight out multiplication and or division. You only distribute when there is addition or subtraction present. Multiply here, multiply there, you got this. This is without distribution, of course, as we already said, you get down to here. Divide by 28 on each side. That's it. That solves the problem. That solves it. That's it. You also could have done this. You could have said, okay, he did what he did here. Is there another way to do this? As you know, guys, there are usually numerous ways in which this can be done. So take this guy right here and multiply by a number that knocks out everything. What's 5 times 4? It's 20. Let me multiply by 20 on each side. Let me take 7w over 5 minus 3/4 equals 0. I wonder if this is going to work. If you multiply by the same thing on each side, it's still an equation. If you take this and go over here and then go over there, now 20 is the same as 20 over 1. We got 20 over 1 times 7w over 5, and you got 20 over 1 times 3/4. And you got 0 times 20 over 1, or 0 times 20, and that's 0. Notice you don't have the 20 over 1 getting diminished. That's a subtraction at the end. Leave it be. You don't have the 20 over 1 getting diminished at all because you are fully distributing the quantity 20 over 1, or 20 if you want to call it that. Same thing. You are fully distributing the 20. You're fully distributing the 20, so you get to here. 5 goes into here. Four times 7W is 28W. 1 times 1 on the bottom, and it goes into the top. We know it just stays as is. Same here. 1 times 1 on the bottom, it goes into whatever you got here. 5 times 3 is 15 equals 0. Add 15 on each side. That's out of there. You got 28W equals 15. 28W equals 15. Divide by 28 on each side. Looks familiar. Yeah, it better look familiar. If I'm claiming the mathematics is valid, regardless of the way I choose to do the solution to the problem, regardless of how I choose to get the solution to the problem, if my mathematics is valid, then no matter how I do it with the valid mathematics, whatever the mathematics may happen to be, a little different look, doesn't matter the different looks you give, you better be getting the same answer. And we are getting the same answer. I can't always do that to show you multiple ways. It takes a lot of time, but this is kind of an illustration of some things that go on. Approach this in different ways and get the exact same answer. If you don't get the exact same answer, something's wrong. Something's wrong. You should be getting the exact same answer if your mathematics is valid, regardless of the methodology that you're using. You might use different methodology, as we did right here, 2 different methods, and we still got the same answer. Very important. So that's kind of the way that this stuff all kind of plays out. The second way we had kind of done it here, multiplying by the same thing on each side, seems to be a really strong method to do because sometimes the matter is so complicated that it's not going to lend itself that easily other than when you multiply by the same thing on each side. And so this second method right here sometimes is the best way to go because the problems get a little too complicated. That's probably the case for a problem like number 2 when we looked at this. So let's stay with this. Let's stay with the second methodology there and see what we can say about it. See what we got here, guys. Here, I'm probably going to multiply by the same thing on each side. There's some interesting points that need to be made. There's some interesting points that need to be made. I'm going to multiply each side by something that's going to knock everything out of the denominators. It's probably the easiest way to go. Now, you got to watch out. I don't know, sometimes you can pick up solutions that aren't valid. They're called extraneous solutions. You may do manipulations with the equation, which are fine manipulations to do, and yet you get into trouble at the end when you give a final answer, because that final answer may not be valid. May not be valid. What do you mean? Well, if I got an answer of 0 right here after I did all the manipulations, there's a problem. It's called an extraneous solution if I did get a number that wouldn't work in the original. Why would 0 not work in the original? What's 4 times 0? It's 0. 1 divided by 0 is undefined. If that's 0, what's 2 divided by 0? It's undefined. it's not really valid. So you may have picked up an extraneous solution. They're probably not going there. That's probably not going to be a problem. So let's not worry about it too much. I don't think it's going to be, but we know. You can't have, you're not allowed to have y. Y is not equal to 0. If you pick up y equal to 0, you picked up an extraneous solution, and it's not valid, not allowed. Tell you what I'm going to do. There's a 4 here. There's a 4 here. There's a y. There's a 6. There's a y. There's a 2. 2 times y is 2y, but it ain't going to make it here. 4 times y times 6 is 24y. That cancels everybody. I might have an easier way to go. Does 4 go into 12? Does 6 go into 12? Does 2 go into 12? Does 1 go into 12? I could use 24y. If I'm clever about this, I got a feeling 12y is the best to use on each side. 12y is the same as 12y over 1. 12y is the same as 12y over 1. I'm picking something that all the bottom things go into. All the denominators go into. Does 4y go into 12y? Does 6 go into 12y? Does y go into 12y? Does 2 go into 12? Sounds good. I could have gone 4y times 6 and got 24y. That would have worked. And you know, if you're not comfortable, then do that. Then do just that. The big thing is take this and go here, then go there. Take this, go here, and then go there. It's a big move to make. Once you make that, you're looking pretty good, guys. We got 12y over 1 times 1 over 4y. All right, that's good. That's good. Let's see where this is going to go, guys. You know where this is going to go. You know how some of this stuff plays out. Let's go. 4y goes into 12y 3 times. 6 goes into 12y 2y times. Y goes into 12y 12 times. And 2 goes into 12y 6y times. There's a lot of stuff there. There's a lot of stuff there. Let's do it. Notice there's 1's all underneath. The 1's are all in the denominators. 1 times 1, you multiply 2 denominators, 1's 1. One of them is 1 and the other one is 1. You multiply the 2 denominators, 1 times 1 is 1. 1 into anything is just the anything. So the denominators are basically out of there. Let's see what we got here. This one right here, you got 3 times 1 over 1, that's 3. You got 2y times 5, that's 10y over 1, that's 10y. You got 12 times 2, that's 24 over 1, that's 24. You got 6y times 5, it's 30y over 1, it's 30y. Let's cut to the chase, guys. So basically you got this. You got this. Let's just make sure we know what we're talking about. Let's make sure it's on. Equals 24 That's it. Minus 30y is plus the opposite of 30y. Sounds good to me. You do a whole bunch of things here, guys. Let's add a positive 30y on each side. Negative 30y and positive 30y is 0. Let's add 30y on each side. The 3 comes down. The 40y is this. The 24 is this. We got that. Let's subtract 3 on each side. Equals 21. Looks pretty good to me. Well, we didn't run into the trouble of maybe the y ended up being 0. Well, that's a solution that we're not allowed. This looks good. This looks good. So we got it. Looking good to me, guys. So we got the 2 right there for number 2. Let's look at 3. Now this one, again, lends itself a little bit easier. It shouldn't be quite as convoluted as what could happen. And in fact, it's not as convoluted as what we just did. Just kind of be careful. 6 is 6 over 1. This is that. I'm just going to cross multiply, guys. I think this one lends itself pretty easily to it. 1 times all this is just all this. 6 times 2 is that. Minus 1 is plus a negative 1. 3 times big H, 3 times negative 1, and 12 is 12. Not looking too bad. Let's add a positive 3 on each side. That's out of there. 3h well, I mean, that's a good point. Divide by 3 on each side, right? H equals 5. Let me kind of polish that up a little bit. I don't think it really matters, but I'm always, the way this stuff is always filmed, sometimes you got to watch it a little bit. You get down to here. From here, you take divide by 3. H equals 15 divided by 3 equals this. Absolutely correct. So we got that one. So that's 2 and 3 on that one. Let's, I've seen some of this already. We had the 15 over 28. We had the 21 over 40. We had the 5. Sounds good to me. Let's get the 4. 4, an organ pipe of length capital L feet emits sound at a frequency of n vibrations per second. N is equal to 1100 divided by 4L. What length is required for 50 vibrations per second? Okay. Pretty straightforward stuff, guys. Shouldn't be too bad. All right, guys, for number 4. They're saying, like we said, an An organ pipe of length capital L emits sound at a frequency of n vibrations per second. N equals 1100 divided by 4L. What length is required to get 50 vibrations per second? This is the equation with which we will be dealing and consulting. They want to know what length is going to get you to that. Well, if it's n vibrations per second, you want to get it to 50. They basically want it to be, they're asking if n is 50, what kind of L are you talking about? If n is 50, there's a number of ways you can do it. You can solve it flat out symbolically without too many explicit numbers being written down, and then later on plug in appropriate numbers, or just go with what I'm doing right now. If you get it to here, well, I mean, like I said, at that point, it shouldn't be too bad of a move. There's a number, you can just multiply by 4L on each side or just do cross multiplication. 50 is the same as 50 over 1. 4L times 50 is 200L. 1 times 1100 is this. This divided by this is 5.5. That's what we're getting. According to the mathematics, let's just make sure where everybody's agreeing with everyone else. 5.5. Yeah, 5.5 feet. Very good. That's page 1, guys. Let me go further. That was page 1. Go on to another page as well and see what we can do, and then try to figure out exactly what I want to do here with this, guys. There's chapters 4, chapters 5, chapter 6, and then we can kind of take it from there. Okay. A lot of ways to go, guys. I'll try to pace this. I'll see how many films I'm going to make related to the final exam. Let's at least here, let me just keep going. We are talking about some chapter 4 content on the second page, and let's try to go through the second page on at least this film. I think it might be a good idea. All right, guys, page 2 of the practice test right now. Let's see some of the stuff they're talking about. It's pretty straightforward stuff. Solve for W for this one. Number 1, 5.09 over 2.47. Here we go. I'm just going to use cross multiplication. I didn't have to do that. I could multiply by W on each side and multiply by 2.47 on each side, and that works too. I could multiply by 2.47 on each side, and I could multiply by W on each side. It works the same way. Here you go. You got 5.09 times W times 2.47 times 9.35. The rest should be pretty basic, guys. Once you get to this point, you should be able to finish this whole thing as it needs to be finished. It's about as simple as that. Once from there, that we can manage. So let's see what we got here, guys. We got a lot of ways to go. I mean, you could say, okay, you can leave this as is, and then go 2.47, 9.35. Yeah, right. 2.47 times 9.35 23.0945. Let's go. Divide by 5.09 on each side. Correct, right? Okay, yes. Yeah, they got a lot going on here. I don't know how far they want to take it. Did they really specify that, actually? 4.53, 72298. 7229862. At the 8, I'll round it up to here. I don't know where they want to go. Well, we'll say they wanted to go there. Let's see how much they wanted to do. Number 1 from chapter 4. They got W equals 4.54. Makes sense. So here they just round it. Usually they're rounding to the nearest hundredth. We'll use our best judgment when we're doing that. Rounding to the nearest hundredth, that 3 goes up to a 4. W equals 4.54. So there you go. Number 2. If a student got 19 correct on a 23 problem test, what percent were correct? Okay, pretty straightforward stuff. They got 19 correct out of 23. What percent is that? Well, let's get a decimal expansion related to that. 0.82608, 0.826086, so I'll say 0.82609. I rounded this one, but it was an 8, 0.826087. I don't know that I needed to do that, but let's do it. Let's go 2 places over. Let's call it 82.6087. 82, yeah, right. 82.6087%. Round that to the nearest. I don't know where they're rounding that to. So let's just. Nobody gave us any specificity on that. That shouldn't be a problem if we just watch what we're doing here. They went to the nearest whole percent, so I have no way of knowing that would have been the case, but that's okay. 2 is 83%. Rounded to the nearest whole percent. The 2 goes up to a 3 because of the 6 right here. And we've got this as an answer there. Sounds pretty good. That's 2. Let's talk about 3. 500 feet of aluminum wire weighs 15.2 pounds. Find the weight of 180 feet. There are a number of ways to go here. They're all going to work, but you got to know what you're talking about. The first thing you do if you're going to talk about something like this is, what do your instincts tell you? What does your common sense tell you? What does your basic mathematical knowledge tell you? Look, if 500 feet of aluminum wire weighs 15.2 pounds, if all other things equal, just the length can be different. The thickness of it, the density of it, all that is the same. The thickness of it, cross-sectional area, meaning thickness, I guess you could say. The cross-sectional area is the same, the density is the same. Only thing that's going to vary here is length. if 500 feet of aluminum wire weighs 15.2 pounds, if you were to double the length of wire present and bring it to 1,000 feet, well, if it's 15.2 for every 500, if you double 500, you're going to double the 15.2 pounds. 15.2, 500 feet gives you 15.2 pounds. Double that, 1,000 feet, gives you 30.4 pounds. Sounds good to me. How about 10 times that? Well, 10 times 500 is 5,000. It'd be 10 times the 15.2 pounds. 10 times 15.2 is 152 pounds. If you go the other way, if you go half of 500 feet is 250 feet. That'd be half of 15.2. If you do the math on that, that's 7.2. Half of 15.2 is 7.6 pounds. So on and so forth. So I want less feet. I want less of it. Maybe it's about a third of it. Well, it's going to be about a third of the weight. So there's a lot of ways to do this, guys. There's a lot of ways you could play the game, but you got to do it right. You already know it's going to be a smaller number than 15.2. If you set up your proportion incorrectly, your instinct already tells you don't do that. You better not get an answer bigger than 15.2 pounds if the length of wire is nearly a third of the length that was originally present. If it's nearly a third of what was originally present, it's about a third of the weight, about 5 pounds or so. 5, 6 pounds, whatever. It ain't more than that. So you want to just look at it. You want to look at it from the standpoint of common sense and say, okay, well, there's a lot of ways to go here, I guess you could say. You could say every 15.2 pounds is associated with 500 feet length. How many pounds are associated with 180 feet length? Pounds per feet, pounds per feet. You could also do this. Tell you what, 180 feet of length compared to 500 feet of length, small divided by big, is going to be a small weight compared to the big weight of 15.2. This is another way you write this. There's other ways to write this. There's more ratios that you could put together. When you take two rational expressions and set them equal to each other, they're called ratios. You take two fractions. A ratio is the fancy word for a fraction. You take two fractions, you set them equal to each other, you have a ratio. Short length compared to long length, small weight compared to big weight. Sounds good to me. I go 500 times x. I go 180 times 15.2, which is interesting in its own right. I mean, I can almost do this in my head. I don't know, I'm probably pushing it here. Let me see what I got. I got 1,800, half of that, 2,700 right there. 2,700 plus 36 is 2,736. If you take this, don't know if that's the right answer. I got a feeling it is, guys. There's some tricks to doing this. If I divide both sides by 500, again, we said the answer is going to be about 5, 6, whatever. The 500 goes into here. There's a trick to this as well, I guess you could say. The 500 is going to go into here how many times? I want to make sure we actually even got the right thing going on here. For some reason, I'm almost afraid I'm not doing this right. I think we're okay. We got this right here. If it was 1,000, it'd be 2.7. If this was 1,000 down here, it'd go into here 2.736. It's going to be double that because you're dividing by something half as big. So it's going to be 5. Let me see here, guys. Trying to get an answer here. You would be doubling the 2.736. You get 5.472 pounds. Well, that's the claim I'm making. Hopefully the math is right. I'm kind of freelancing a little bit. I hope I don't have to go back and redo it. If so, it's only a couple minutes that we lost. Hopefully we don't, but let's have a look at it. I'm getting this, and then you got to just round off. What we got here is number 3 for that. They got 5.47 pounds. I got 5.472 pounds. Okay, that's just a matter of a round off. They're rounding 100th. Well, there's only a 2 right there. So the x is 5.47 pounds. Sounds good to me. That's the answer. Just for the standpoint, kind of looking at the beauty of the mathematics, I guess you could say, guys. Are we looking at the same answer had you done this? Darn right you are. 500 times x is 500x. 15.2 times 1800 is 15.2 times 18. Look, guys, even though the fractions are different, notice how we're getting the exact same result of cross multiplication. You're going 15.2 times 180 to get this. You're going 500 times x to get this. That's pretty fascinating stuff. Either way, that right there came from 500x equals, here we go, 500x and 15.2 times 180. Well, that's the same thing as that. Come the same thing as that. All right, guys, that's the so far so good as we look at this. Problems 4 and 5 related to the related to the review for the final exam. Problems 4 and 5 from chapter 4 are also to be found. Let's look at them. So we just did number 3. Let's do 4 and 5. Number 4, in an alternating current circuit, capacitive reactance X sub C is inversely proportional to frequency F. If X sub C is 80 ohms when F is 400 hertz, find X sub C when F equals 1,000 hertz. Okay, there's, this stuff is, guys, so much of this stuff, you guys, is easier done than actually explained or initially looked at. So let's kind of look at it and see what's going on here. Read number 4 and we'll get down to it. We'll figure out what they're talking about here. All right, well, let's talk about this without talking about it as much as we could talk about it, I guess. Let's just say a few things. In an alternating, number four, in an alternating current circuit, capacitive reactance X sub C is inversely proportional to frequency F. If X sub C is 80 ohms, when F is 400 hertz, find X sub C when F equals 1,000 hertz. Well, this gets a little messy. Don't know what to say. There's a lot to be said here. We will say that, for our purposes, X sub C, capacitive reactance, is equal to some constant K over frequency. The bigger the frequency, the less capacitive reactance, the less ohms associated with the final answer. The bigger that F is. The bigger that F is, X sub C gets smaller. The smaller that F is, the bigger that X sub C becomes. So let's put it that way. I don't want to go into this beyond that too much. I mean, they're not going there. I'm not going there. Let's just leave it at that. If this is the case, the k is going to be a constant in all instances for this particular problem. If x sub c is 80 ohms, I'm just using that right now. If x sub c is 80 ohms, and here's the k, right? We said it's a constant. When this guy is 400 hertz, find x sub c. Find x sub c when f is 1,000 hertz. So I want to find x sub c when they're already giving me this. Now there's a number of ways to go here. I'm almost wondering if the easiest way to go is solve for that capital K. And then solve for the capital K up here, then put that answer for capital K right there. Let's take this guy. Let's multiply by 400 on each side. No, the top one now, top here, right? Multiply by 400 on each side. When you multiply by 400 on each side, the 400 cancels out, and you got K. K is going to equal, not worried about units right now, guys. 8 times 4 is 32. That's what K is. Tell you what, I'm going to put that right there. There's other ways to do this, and we can explore it in person if you wish. But right now, we're exploring this. 32,000 divided by 1,000, 32 ohms. That is smaller than 80 ohms. It makes sense. The frequency is bigger. When the frequency gets bigger, you're going to get a smaller answer. Another way you could have done it is this. Big capacitive reactance divided by small capacitive reactance is the same as, well, it's an interesting point. You could, that's it. That's the end of the story. You're done right there. It's 32. Let me just kind of give you another look at it, though, if you don't mind. We can say, you could have played it like this. K over 400 is a big answer. Really? 400 is a big division. Yeah, compared to the division about to happen, it's pretty big. That's a big capacitive reactance. Why? Because 400 is not as big. 400 is small. It's not as big as the 1,000 on here. You divide by 1,000, you get a small answer. You're going to have a small capacitive reactance when the guy on the bottom is big. You're going to have a big capacitive reactance when the guy on the bottom is small. We already know that 80 is a big number compared to what the answer is going to be for the other one, because the other one's got a big thing on the bottom. So this is big divided by small. This is big compared to what's going to happen here. Well, if you do this monkey business, a fraction divided by another fraction, these flip and you get 1,000 over 400 equals 80 over x sub c. This thing, 400. 1,000 divided by 400. This reduces to a lot of stuff. If you do the reduction, this goes into here. 400 goes into 1,000 2.5 times. Half over 1 is the same as 5. You could play the game this way if you want. 5 times x sub c, 2 times 80, 5 times x sub c. 2 times 80 is 16. Forgive me, 160. 2 times 80 is 160. 5xc equals 160. This goes into here 32 times. That looks awfully familiar. Again, you were done 5-10 minutes ago. If you go this way, you can get it. But this is kind of the way you want to look at what's going on here. This whole idea of an inverse relationship. It's a hard thing to understand. It's a hard thing to explain sometimes. When we do more of these, you get more of an instinct as to how to do it. But that's something pretty important and worthwhile talking about, definitely. That was number 4. Let's go to number 5. Number 5, the weight W of a substance is directly proportional to its volume. Makes sense to me. If the density of the material remains constant against all situations, or in relation to all situations. In all situations that are being considered, the density of the object remains unchanged. In all situations, the density of the object remains unchanged. If that's the case, the more volume you have for that same substance, if you triple the volume for that same substance, same density, if you triple the volume, you're going to triple the weight. If you make the volume 10 times what it was earlier, it's going to have 10 times the weight. The more substance that's present, the more it weighs, all other things held equal. Makes sense to me. Number 5, the weight W of a substance. The weight W of a substance is directly proportional to its volume V. If W equals 180 grams when V is 30 cubic centimeters, find W when V is 100 cubic centimeters. Sounds good to me. Let's talk about it. The weight W of a substance is directly proportional to its volume. More volume, more weight. Less volume, less weight. Makes sense to me. You can go a number of ways here, guys. Let me try to be somewhat efficient about the whole thing. I'll just say volume big volume, over volume small is proportional to weight big over weight small. Big volume compares to small volume the way that big weight compares to small weight. Let's talk. If, now we got to find out who's who. Well, we already know. V is 30 cubic centimeters, and there's another V that's 100 cubic centimeters. I'm going to compare 100 cubic centimeters to 30 cubic centimeters, which is less than a third of what that is. This one right here is more than 3 times that. Well, the weight associated with it is going to be more than 3 times that also. If this is more than 3 times this, the weight associated with big weight. So I'm going to find the weight, big, I got to call it W sub B, it's big weight, compared to the small weight. The small weight, they told us, was 180 grams. That's it. Could you have flipped this around? Yeah, make sure you flip that around or else you're going to get it wrong. Could you have done other ratios? Yeah, there's at least 2 other ratios you could do beyond all that. There's about 4 ratios you can throw up here. I just simply said, look, Big volume compares to small volume the way that big weight associated with the 100 compares to small weight, the one associated with the 30. Thirty times WB yeah, looks pretty good. I have a 30 on each side. You know, wheel and deal with the mathematics a little bit. Yeah, I can believe it. I can believe it. I mean, if it's a bigger volume, if it's more than 3 times the size of the other one, the weight's going to be more than 3 times the size of that. Well, more than 3 times the size of 180 is more than 540, because 3 times 180 is 540. This is more than that. It's believable. It's believable. Yeah, should be fine. Yeah, 600 grams. Chapter 5 type stuff. Let's take a look at it. From then on, I guess you could say, right? Chapter 5. So let's go to it. They are saying here, again, these are very, you know, they want you with a calculator. I mean, some of these you're going to need a calculator, obviously, but let me, let's just make sure we got it. I mean, so here they're going a little bit into the chapter 5 stuff. I'm still on the second page of the review exam. Here's the chapter 5 stuff. And they talk about a few things here. Let's us talk about it too. 1 acre. 1 acre is 400. 1 acre is 4.356 times 10 to the 4th square feet. 1 acre is 4.356 times 10 to the 4th feet squared. How many acres is 9,000 square feet? Well, let's figure this out. I mean, maybe there's a little easier way to do this. Maybe a little easier visualization. There's nothing wrong with the mathematics here. I believe what they're saying here. Let me do something about this. Let me take this and multiply it by 10 to the 4th and get this. It's a little easier to look at because they're giving me the 9,000 as is. What does your instinct tell you? Before you do all this as you should do it, and you get down to here. Now, what does your instinct tell you? What does your instinct tell you regarding that? Well, my instinct tells me they want me to know how many acres is 9,000 square feet. It's a reasonable question. Well, wait a minute. If 1 acre is this many square feet, which is a lot, 43,560 square feet for 1 acre, 9,000 square feet is about 1/4 or 1/5 the size of this. So it's probably 1/4 or 1/5 of an acre. If a whole acre is this many square feet, and the 9,000 is a relatively small fraction of this, the 9,000 is anywhere between 1/4 and 1/5, probably closer to 1/5, probably closer to 1/5 of this quantity, it's going to be about 1/5 the acreage. In other words, if you're going to say to me, there's a lot of ways you can do this. As I said, there's a lot of ways you can do it again. I would say to you, small amount of square feet compares to a large amount of square feet is a small amount of acres compared to a big amount of acres. One doesn't look too big to me. 1 acre is big compared to what 9,000 square feet is. A few square feet compared to many square feet, an equivalent amount of acres, which are small, compared, small divided by big is small divided by big. That's got to be the big one. You can't go 1 over x. You're going to get it wrong. You also could say, well, look, 43,560 for every 1 acre. 1 acre is associated with 43,560. How many acres are associated with 9,000? Look like 2 different ratios here. Yeah, I guess they do. When you do this cross multiplication, you get 43,560 times x equals 9,000 times 1. That's it. You got to solve for that and you're there. So, well, I don't know. I didn't start with that. I started with this one, like you initially told me to start. Be my guest. Be my guest. This times that is that. This times that is that. It doesn't matter. It doesn't matter how you set these up. As long as you set them up correctly, the cross multiplication, very surprisingly perhaps, ends up being identical regardless of what 2 ratios you are dealing with. Regardless of the ratios with which you are dealing, you're going to have the same cross multiplication occurring. Very interesting how that works. So we got this. 43,560 times x equals 9,000. 43,560 times x equals 9,000. $9,000 divided by 43,560. .20661. Right. Trying to say, yeah, 0.20661 acres. Yeah. That's about a fifth. 0.2 is 2/10. That's about a fifth. It made sense, guys. Don't go getting answers that are bigger than what you initially had. Oh, it's got to be 5 acres. How on earth would it be 5 acres? It's the reciprocal of 5 acres, 1/5. 0.20 something, or something close to that. How on earth would that be 5 acres? If 43,000 something is 1 acre, and 9,000 is proportionally, 1/4, 1/5 the size of that, the acreage is 1/4, 1/5 the size of that. It's like me saying I have a $100 bill. What's its value? Well, it's a $100 bill. How does a $20 bill compare to it? It must have 5 times the value. How on earth would it have 5 times the value? It's 1/5 the size. Same thing here. The 9,000 is a small ratio, relatively speaking, of the 43,560. And that's where that stuff's coming from. Let's see where, how they gave the answer. The guys, you've seen these in these films thus far, that I'm always apprehensive of how I'm giving the answers here. They're going 0.207 acres. They're going right here. That 6, does it stay a 6 or go up to a 7? If it's 5 or more next to it, it goes up to a 7. Sounds good to me. That's fine. I mean, I'm not going to nickel and dime you on decimal answers to a large degree, unless there's depends who's watching the film here, guys. I mean, you know, for those of you in my physics classes, there are certain things that have to be done according to the rules here. For our class right here, in a large array of circumstances, there's a little bit of flexibility I can afford. But the big thing is, okay, we got an answer here. X equals 0.207 acres. Absolutely. So let's see here, guys. Let's see how I did that. That was number 1. Okay. Let's stay with chapter 5, you guys. Okay, so we got that. Let's look at number 2 on that. They got some stuff here, rounded nearest tenth. We get the answers here. These all should go pretty straightforward, you guys. Don't be. See exactly what we can say on this stuff, and we'll kind of take it from there. For 2, they're saying, let me give you R, or let's you guys tell me what R is. We got 3.14 on the bottom here. D, F1 minus F2. Again, they're just trying to get us acclimated. They want you to find what R is. Find R when you got H is 46.3. D is 5.72. F1 is F2 is round to tenths, bring it to the nearest tenth. Okay. The rest, guys, is you're just plugging in the values here to see what you can say on this thing. So let's just make sure you got it in parentheses. When it's supposed to be in parentheses, deal with what's in parentheses and go for it. Let's see what we got. I will take the top and go 33,000 times 46.3. There's a number of ways you can play this. Just plug in the values, get a final answer here and divide it into the top, or you can individually divide each one of these in there. You got to be careful if you do that. But so just, you go for it the way you know how to go for it. Let's just make sure we're getting the right answers here. Okay, I'm getting, at the end of all that, again, extreme caution is always needed on this stuff, guys. I got 68.05488. Right, 68.05488. See how far they were looking. I think they said round to the nearest tenth. How am I not paying attention, guys? Okay, so is that going to stay a 0 or go up to a 1? Again, let's just make sure the mathematics was done. It's easy. You know, we know what we're doing, but again, at the end of the day, the answer has to be right. We have to be getting the right answer there. So 2 is 68.1 according to what we're doing. Right, 68.1, that's fine. Okay, very good. That's 2. Let's look at 3. Find C when H equals 75.3. Find C when big H equals 75.3 and small h is 91.8. Round to thousands. Okay, not too bad. This stuff is pretty straightforward, guys. Just got to be careful. Let's not be careless when we do this stuff, and we should be okay. We got to here. Let's find C. They said round it to the nearest thousands. This is 1. This is 1. Big H small h just do this and let's see what it tells us, and we'll take it pretty far out if we need to. We need to take it to the 10,000s place. We're rounding to thousands. See how this all plays out. Right. C is 0.423955. 0.423956 tenths, hundredths, thousandths. Let's round it up. Does that stay a 3 or go up to a 4? It's going to go up to a 4. Let's make sure. Pretty confident with these guys, but you know, like I said, C equals 0.424. Sounds good to me. So we got that. Number 4. Find capital Z when A equals 5,000, R equals 0.085, T equals 2, P equals 5. Round to hundreds. Okay, telling us a lot of stuff here. This is what you're dealing with. That's Z. Now, I'm, of course, going to write it smaller at the end. Not sure why I wrote that as large as I did, but here it is. So this is the one we're getting. And here's A. Here's 1 plus R over capital T. This is PT. Okay. What we got here is, okay, let me shrink that down to size, guys. We've got A is 5,000. Got 1 is 1. We've got R is 0.085. R is 0.085. T is 2. P is 5. P is 5. And T is 2. So I'm going to find what 5 times 2 is. It's going to be 10. And then I'm going to exponentiate this quantity right here. That's it. Not putting him in here and then exponentiating. Just this right here is going to be taken to the 10th power, 5 times 10. Only this right here is going to be taken to the 10th power. When you're done, then you multiply by 5,000. Well, okay. I mean, it sounds good to me. So what we have here, let's add these two together. And we got 1 plus this, which is going to be, well, this divided by that is going to be 0.0425. That thing's going to be taken to the quantity 5 times 2 power. It's going to be taken to the 10th power times 5,000. There we go. Z is going to equal 7,581. 7,581.07234. Well, 0.07 and the 2 right next to it doesn't do anything to it. I think, what did they say though? Did they say thousandths or hundredths? Let's see here. Just to the hundredths. So 0.0, yeah, that's fine. That'll work. $7,581.07. Let's see where we are, guys, here. 7,000, yeah, right. It's supposed to be Z. I don't think they're solving for, they got X here, but it should not say X. It should say Z. Not a big deal. Z equals 7,581 and 7 hundredths. 7,581.07. 7,581.07. $7,581.07. Yeah, they got that. It's the same thing. Again, I just want to make sure they were asking. I'm almost sure they're asking for Z. That's not going to be an issue. Find Z. Yeah, so that's fine. Okay, number 5 is something associated with the graphing calculator, so we'll just go with the answer that they have on here, guys. For number 5, select one of the following. For number 5, select one of the following viewing rectangles that give the best complete graph of y equals negative 2x plus 14. The best selection will be a range that shows the graph crossing the x and y axes. Where that will happen the best, you guys, for number 5 is choice C, and that would be the very last one. So they're saying here for number 5, depending on what kind of graphing calculator we're using, but that's for right now. Let's just make sure. The best one's going to show is going to be a window that has the x-axis being crossed and the y-axis being crossed when you're being given this. Y equals negative 2x plus 14. Well, it's got to be pretty high up there. The other ones don't, 14 is pretty big. To be crossing the y-axis, you've got to have a y max that's pretty big. And the one that has the y max equal to something pretty big. That's the biggest y max I can find. The other ones don't have the right y max. There's a y min and they're saying negative 5. They want to see, they want to see the x-axis being crossed. And x min, x max x min is negative 5 for a comparison. X max is 10. So we're looking at the x min being that, x max being that, y min this. Y max, it kind of needed it to be pretty big. The other ones didn't really offer that option. So that's that. Let's go a little bit to chapter 6 type content, and they want us to take the answer, a couple things here and round it to the way they want to round it and everything else. You're looking at significant figures. The number that has the least significant digits kind of calls the shots. It's going to be 4 significant figures for problem number 3, just to give you a heads up. We're not even at that problem yet, but something to kind of be looking at here for number 3 with 6 over there. So, right, so you need 4 significant figures and you're going to have it there when we do it. Okay, let's look at that situation. Let's look at the chapter 6 and finish it off from there and take it from there. All right, guys, let's take 6 here. Let's take a look at it and see what we can say related to it. For number 6, convert 100 kilometers per hour to miles per hour, round to tenths. It's kind of don't have the chart in front of me right now. I can look it up. I'll just go with what I know. You can think on the fly on this one, guys, and make it happen. Again, for the chapter 6 part of the review, convert 100 kilometers per hour to miles per hour. Fascinating question in its own right, I guess. 100 kilometers per hour. Tell you what I'm going to do, guys. There's different values, I guess, you can get on these things. Roughly 1.6 kilometers, 1,600 meters, is a mile. A closer approximation is, again, I'm going to, push comes to shove, this doesn't go right, I'm going to go to the chart, but let me go with this. 1 mile is 1,000 1 mile is 1,609 meters. 1 mile is 1.609 kilometers. So 1 mile is 1,609 meters. 1 mile is 1,609 meters, which is the same as 1 mile is 1.609 kilometers. An hour is an hour. Well, this is important. Every mile is associated with 1.609 kilometers. Every 1.609 kilometers is associated with a mile. Each of these is a ratio of 1 over 1. 1 over 1? Sure don't look like it. Saying $100 is the same as $100 bill. $100 over one $100 bill is the same as one $100 bill over $100. It's a weird one. Doesn't look like one, but the units don't look alike either. That's why when it was said and done, it's the same amount of money top and bottom. It's the same amount of distance top and bottom. So that's pretty interesting in its own right. Tell you what I'm going to do. I'm simply going to take and multiply by a special one called 1 mile, because I want miles on top. 1.609 kilometers on the bottom. Sounds good to me. You're basically going to get 1,000 divided by 1.609, and you're going to get miles. Let's see what happened. One thousand divided by 1.609. Yeah, that'd be 621. 1,000 divided by 1.609 would be 621. We're not talking about jets, though. I don't know where I got 1,000 on this one. Did they say it was 100? Okay, yeah, my fault. That's all right. The conversion factor is the same. That's 100. I don't know where I got 1,000, unless we're talking about fighter jets or something. Let's do it. Well, if you do the division, 100 divided by 1.609, 62.1504. True. Let's see what kind of answer there. We're saying round to tenths, huh? Round to tenths. That one goes up to a 2. Now again, they might be using a different conversion factor that I'm using. I don't think so. I think everybody's in agreement here. We got 62.2 miles per hour. Now watch me be wrong on that, but again, we got the argument right. It depends what conversion factors you're using as well. Yeah, okay. Well, yeah, see, they go either way here. It depends what you want to use. They got 62.1. They got 62.1 miles per hour or 62.2 miles per hour. So there are other ways we can get an answer here. There are other ways we can do this and get the answer really, really close to what we want it to be. That's probably why they have 62.1 miles per hour as opposed to 62.2 miles per hour. In fact, they've got both of them down there. 62.1 miles per hour or 62.2 miles per hour. It's good enough. Good enough. Let's go to 2 and 3 regarding all this. 2.5 milliseconds to get you seconds. Give me seconds for that. So let's see here. We got this. That's fine. .5 milliseconds, how many seconds is that? Well, every millisecond, it's kind of interesting in its own right, I guess. Every 1 second has 1,000 thousandths of a second. A millisecond is 1,000th of a second. So 1,000 1,000ths of a second is 1 second. So basically, every 1 second is 1,000 milliseconds. Because a millisecond is 1,000th of a second. So 1,000 times 1 over 1,000 gives you the second. Or 1,000 milliseconds for every 1 second. Again, this is a special one we were talking about, similar to what we did over there. They're asking here, 2.5 milliseconds, how many seconds is that? Well, 2.5 milliseconds, get seconds, choose the one that's going to give you seconds here, over every 1,000 milliseconds. They cancel. 1,000 goes into here, 0.0025 seconds. Wow, it's not a big number. Yeah, it's not a big number because the second is a big unit. So you don't need as many of them to describe the small unit of the millisecond. Okay, so that gives you that. .0025 seconds. Good enough for me. Let's look at number 3. All right, guys, they're saying for this one, get the right units. Well, there are the smallest amount of significant figures determine what the answer is going to be looking like. This has the 41.63 has 4 significant figures to it. This one right here has 5 significant figures associated with it. Well, that's too much. I mean, if 4 significant figures are going to call the shots, at least on the top, if that was all you had, well, you got more going on here. Here you got 4 significant figures as well. That's as small as it could get, guys. I mean, the 4 significant figures is about as small as it's going here. Because this guy right here has got 5 significant figures also. But that's, yeah, okay, that's great that it's there. 7.0358. 5 significant figures, 5 significant figures. The 4 significant figures calls the shot. So I'm going to have 4 significant figures at the end of this thing. Let me grind out the mathematics and just round it to the, have 4 decimal places in there, or 4 significant figures, probably a better way to say it. Well, in this case, I guess you could argue, depending on how they've actually reported the answer here, guys. The 5290 can also be just 4 significant figures if there's nothing in front of this that was being dealt with. This is kind of arguable, but again, what's calling the shots here is going to be the 4 significant figures. So what we have here is 41.63 times 0.0529. I got 0.807958. Four significant figures are going to call the shots. 1, 2, 3, 4. Does that stay a 9 or go up to a 10? If it goes up to a 10, and it does, it's going to come out to 8080 here, means actually we're faithful to this. You kept it here. And that'll be the answer here. It's debatable what that is. I mean, how you're going to look at it as far as significant figures. We can look at that in the book and kind of discuss that more. At the very least, it's 4 significant figures. And that's kind of what's calling the shots here. This is 5 significant figures, but that's the lower number of significant figures will call the shots on this. So it's going to come down to that. More to talk about on that. I mean, there are subtleties here regarding that. So, so even if it's just 4 significant figures for the 0.05290, they can argue that in a number of ways, I guess. Okay, looking pretty good, guys. This is what it is. We've gotten it to here. These are the first 2 pages in this particular film. Right, okay. First 2 pages in this particular film. Maybe it's worth noting here, guys, if I could maybe add something here to the discussion. You know, they talk about a lot of things with significant digits, pages 269 all the way to 278, or 267. You know, in this section they talk about, in an old tech math book, in this section we will discuss the meaning of significant digits and measurements. We will also discuss rounding to a certain number of significant digits to simplify the instruction. To simplify the instruction, we will not use measuring units in this section. The significant digits in a measurement are the meaningful digits in the measurement. All non-zero digits in a measurement are significant. So 14.4 would have 3 significant digits. 17.4 would have 3 significant digits. 35.96 contains 4 significant digits. Any zero between non-zero digits in a measurement is significant. Okay, so if it's 20.6, there are 3 significant digits. If it's 9.005, that's 4 significant digits. The zeros matter. Any zero before the first non-zero digit in a measurement, any zero before the first non-zero digit in a measurement is not significant. So yeah, I guess when we had, I was kind of a little apprehensive about that. Up there, when we have the 0.05290, the 0.05290, the first zero doesn't count as significant. The 5290 does. If they wrote it down, if they wrote the zero at the end of that, it does have meaning, typically. So let's see what Final zeros after the decimal point are included to indicate the precision of the measurement. Therefore, they are significant. 3.0 contains 2 significant digits. 5.900 contains 4 significant digits. So there is something there. You know, they talk about a lot of stuff here, guys. Zeros before the decimal point may or may not be significant. Okay, zeros before the decimal point. There's some ambiguity there. We got to look at that. So it depends on the precision of the measurement, for example. You know, you talk about 3 significant digits, 4 significant digits, 2 significant digits. State the number. You know, so final zeros before the decimal point may or may not be significant. It depends on the precision of the measurement, what they're talking about. So we got to watch it a little bit, guys. You know, they talk about relative error, absolute error, relative error and accuracy of measurements, guys. There's the idea of which, you know, the absolute error, the larger measurement is better. Relative error and accuracy are, you know, accuracy is kind of like the ratio of, we've done that earlier, absolute error, it's relative error. It's absolute error divided by the measurement itself. Well, the bigger the measurement, if the small absolute error, you guys, small divided by something big is a relative error that's really small. It's very accurate. We can talk about. So there's a little bit they talk about what's more accurate, what's better. Their terminology is not always, or the way they're discussing some of the terminology is perhaps not the best, but we can cross every bridge as we need to do it. Okay, just wanted to go back to that and kind of highlight that a little bit. Okay. We're looking good. Let's get away from this. Let's do some other films related to the final exam. This was final exam review part A. Let's go to final exam review part B.